10:07.
Okay. So, Prakash asked me to give like a sort of general overview on categorical quantum mechanics. So I'm very sorry for those people who have been seeing this for, it must be 273 times. You know, there's some of you here who have seen this, especially those who saw 2 days ago in New Orleans, the same talk. So this will be a slow version of the same talk. What?
That one took an hour and a half.
That was an hour. I know somebody else's slots were 1 hour and a half, but that mine took an hour. I always check time. So for some people, so we started this discussion before. For some people, category theory is a method. Like the way I'm going to present it is slightly more really as an ideology about physics, an ideology on how to start a physical theory. And this ideology is not purely specific to physics. The same ideology could apply to, say, computer science or proof theory or biology or chemistry or whatever theory you want to conceive as a theory of systems and processes. You get systems which you give names, like A, B, C. It can be anything. And there are processes between systems which you also assign a symbol to, say F from A to B. Then you think of a system of type A, which you apply a process to, and as a result you get a system of type B. A key example there is, for example, a quantum measurement. You start with a quantum system, you do a measurement, and at the end you typically don't just have a quantum system. You either have a quantum system together with a piece of classical data, or sometimes when you destroy the system, only a piece of classical data. So clearly A in general is not equal to B. Yeah? And then sometimes you can compose processes. So if I got a non-destructive measurement, I can do two measurements after each other. Here I would already have two pieces of classical data. So this type would actually be compound. Suppose that A is a quantum system, then C would be a quantum system together with the first piece of classical data, together with the second piece of classical data. So you see, these things are typically not equal. Wait, so now what I'm setting up here is basically just the definition. What I'm setting up here is basically just the definition of a category. Slowly. So a category consists of objects, which are just labels. You don't assign mathematical structure to them, it's just a name, like qubit, field, classical data type. These are just names of things. Then you got operations. Operations on system, an operation from which takes a system of type A into a system of type B. Then you can compose these operations. If I got an operation from A to B and one from B to C, then there is an operation from A to C, or a process, or whatever you want. Like, again, there are two different perspectives here. There is a perspective, a more operational perspective, where you think of these things as actual operations. You're working in a lab, you set up your experimental device, this is your operation. Somebody is more interested in cosmology, obviously doesn't want to think in terms of operations, but in terms of processes which are happening out there. So both views admit this sort of interpretation. So we got composition, and typically we also got something which is called the identity on an object. Say 1C, what would 1C do? It would take an object C and just do nothing to it. It's like the doing nothing operation. Obviously if you compose one, if you've got like F from A to B, and I do the identity here, or I do the identity here, the result is just F, because it's doing nothing before or doing nothing after. So we've got objects, morphisms, we can compose them with a composition, and then finally, if I've got object A and object B, which means system A and system B, then sometimes I want to think about two systems at the same time. So I got a system here and I got a system there. Maybe I want to make them interact or something like that. So I need a symbol. I need a symbol to write down that there are two things going on. And typically the symbol we use is this little symbol. Don't think of it now as a tensor product immediately. It's just a general way of looking at two things at the same time. Obviously, if I've got process F from A to C and process G from B to D, then I can also think of process F on A and process G on B doing at the same time. So this gives you a new process. I could also have other processes which are not necessarily, which I cannot necessarily write down as a tensor of these two things. For example, in quantum mechanics, entangling two systems. I couldn't write this down in such a form, like doing something on one system, doing something on another system. So you have this symbol, you have these operations which go from A to B, C to D. Now, basically everything which are, so let's wrap up again. We've got objects, we got processes, we can compose them one after the other, we can compose them in parallel, and this, subject to some conditions I will comment on later, is what is called a monoidal category. So if you look in the textbook of category theory and you look up the definition of a monoidal category, then you will get like a horrible amount of jargon you need to sort of swallow through, things which are called natural transformations, bifunctors, whatever, just to get to this simple definition which is operationally very evident. And I think that that's just a problem with the literature, that people just refuse to present this as a simple whatever concept. Something is being done about it anyway. So, now, so basically, you can completely forget about everything which I've said now. And you can completely forget about all these weird axioms which I'm not going to mention. They're completely unnecessary. Would be good to have some water to dip in. Yeah. This sponge dries out quickly. So there is this thing which is called a symmetric monoidal category. Which you find typically very far in a textbook on category theory, close to the end. While it's a very obvious thing which applies to just general situations where you're talking about systems and processes and composing them one after the other or composing them on different systems. Now the amazing thing about this is that there exists a purely graphical language which is such that whatever you can prove from the categorical axioms of this theory, which I'm not going to mention to you, you can prove in some sort of graphical language. And this graphical language is extremely intuitive. And so for the rest of the talk, I'm just going to refer to this graphical language and you can completely forget about all these symbols. So, how does this go? Well, whenever we have a line like this, we think of it as a system. This is like a system, just nothing happens to it. And this is like a process. So you get a system of type A, you apply a process to it, you get a system of type B. This is composition of processes. Yeah? And this is the tensor of two processes. Very intuitive. So this would be G composed with F, and this is F tensor G. Just the line alone is the identity. We don't have to give a specific state. It's just a line doing nothing to the system. This is doing something. When you see a square box, it means doing something. When you see a line, it means doing nothing. This would be, so if you've got a pure tensor representation, then it's as if you can put a pure tensor in the middle here. Yeah? Like for example, I could also have something of this form, where I can't put a pure tensor in the middle. An example of this would be, where's my sponge?
It's in there. Okay. It's inside
In
the
the
bottle.
bucket.
Oh.
No.
Yeah? An example of something like this, well, an example of something like this would be, I've got A and B, I've got B and A, and I just swap these two systems. I can't write this in this way, so I need these more general things too.
Bob, why don't you use the board to your right? That
Huh?
one. That one. Why don't you use this one while this one dries?
Ah,
You know what I mean.
yeah. I'll never do what somebody tells me, so you should have said not to do that.
Prakash, can we get the old board?
This is the old board repainted.
So okay, where are we? So we've got now this graphical language, and there are two rules which I'm just going to write down. So there is this bunch of actions behind the scene going on, and the main ones are actually the following one, that if you've got something like this, then this is equal to this. This basically embodies what is called bifunctoriality, that you can slide these boxes along the lines and you don't have to care about their height. It's like, it doesn't, if I've got system A and system B, and I want to apply F to system A and G to system B, and they are not entangled, I'm just going to use here a word, then it doesn't matter in which order I apply these operations. That's basically what it says. And then, whenever you've got a crossing like this, I've got F here and G there, then this is equal to doing G here and F there. Yeah? This is all very obvious. You just slide these boxes along these lines. It's sort of very obvious. So since F goes to the other side, you find F here. So this is very intuitive. It doesn't seem to have any content to it. But it's like the basic background definition of a symmetric monoidal category. Now, what is the next step? So this is something which applies to an extreme general. Yeah?
Are you thinking of this as actually drawn on paper or drawn on a blackboard? I mean, you might look at this diagram and say they're the same diagram anyway, so why do you bother to write that equality?
Formally, it's not at all the same thing. Formally, I've got...
Is the crossing a real thing? I mean,
it's a real thing. It's a piece of structure of your...
I mean, the crossing is not just that the two lines miss each other. There's actually...
No. The crossing is formally you would assign a symbol to this.
They do miss each other.
What?
They do miss each other. That's not an interaction.
I mean, could I draw this as well with a sort of...
Wait, let me write it down symbolically.
But it doesn't matter which one goes over or under, is that correct?
Yes.
Yeah.
Yes, this is symmetry. Symmetry means it doesn't really matter. So this symbolically would be...
But part of your structure, the formal structure, or is this crossing?
Crossing is part of the formal structure, yes.
Oh, so it's more than just a category.
It's a symmetric monoidal category. Symmetric monoidal category, and this is symmetry. This is symmetry.
Is symmetry like a natural transformation or something, or does it have some fancy name?
Yes.
Say it again, John, what did you say?
What do you call that? Like crossing? Crossing?
Yeah.
But it's sort of an artifact of the fact that you wrote the systems down on paper.
That's what I was
getting
saying.
to. So you had to have an order to write them down, but
So
in your mind,
this is an
there's no
equational
order.
statement. This is a symbolic equational statement if you want. So it's non-trivial. But the thing is, so you got this axiom of a category, and for those who know natural transformations, so you got some natural transformations going on, of which actually the only essential one is this one. There are other natural transformations like associativity and having units, but they're not at all essential, because the whole idea of passing to a graphical calculus is basically to strictify them, that you can actually treat them as identities. So the only really essential one are the crossings. Now we're going to hear a lot of talks this week where the crossings are not symmetrical. So where you can't just like make them go through each other. Where there will be a difference between this and this. We'll hear a lot of talks about this week. But for the purpose, I'm talking about it like just modeling systems and processes in the plain way. This is enough. You don't need anything more.
Bob, can I repeat Howard's remark, which perhaps didn't hear, which is that the structure, the sigma, appears only as an artifact of the way you're writing things in
Yes.
algebraic form, and really it shouldn't be there at all.
It depends. There are things where you can't avoid it. If you write it down on a piece of paper.
If you write it down.
If you write it down, yes.
Yes.
A lot of the things is about writing. Also, associativity is just about writing down things.
There's a big difference between associativity and symmetry.
Yes, so that's
symmetry.
that's the point I made. The only essential one is symmetry. That's why I don't even mention all the other ones. Because symmetry you can't drop if you write it down on a piece of paper. These pictures you can't just. If you would say in a category symmetry is the identity, so you can forget about it, then your category collapses. There's a much smaller range of models which you could get. So this is one which you can't get away of that easily.
I guess what one could say is that if A is different than B, then sort of it's clear that there has to be a symmetry.
Yes.
If A was equal to B, if there's a symmetry between A and A, well, then you have to write it. It's not the same as the identity, right?
What
But you don't
did
have to write it in this
there?
particular way. You could write it sort of in three-dimensional space and sort of hanging.
Yeah.
But there's still a difference between having symmetry and having none. Right? When you have three A's associativity between them, you can drop. And if the two of them have a symmetry and you drop it, then everything collapses.
Yeah, so if you had associativity, if you had a non-associative category, whatever that is,
Oh.
then you couldn't draw it nicely with a picture. Right?
The picture, the basic theorem about a picture is about what is called symmetric monoidal categories. And they assume that you've got symmetry, natural isomorphism, and a unit natural isomorphism. And then you can, so if you've got these natural isomorphism, there is a theorem by MacLean that you can strictify them. So you can actually drop the fact of them being natural, like real morphism, and replace them by identities. Like,
Except for symmetry, right?
except for the symmetry, you can't do this. So the theorem is any symmetric monoidal category can be strictified with respect to associativity and unit, not with respect to symmetry. So that's why, and these graphical languages exactly represent the strictified version. So there's no, so here, let me show what associativity would mean graphically. So yeah.
So the formal definition is in terms of these equations like you wrote in Julie.
Yes. So the thing is, whatever equational statement in the category you can prove purely by diagrammatic manipulations.
But you have to say something about your collection of equations that get you achieve something, and that's what people call usually a coherence theorem.
Yes.
So that maybe it's useful to discuss that now.
I didn't want to turn this into a tutorial on monoidal categories, and especially coherence theorem is what I didn't want to mention, because that's what get done within the graphical language. So here, let me show the following. What is associativity? What is associativity? Associativity means, in a picture, associativity means that I can either put brackets here, or I can put brackets there, and the result is the same. Of course, in a picture you don't put brackets, so it's trivially satisfied. And the moment it's trivially satisfied, you don't have to care about the coherences anymore, of course, because they're just implicit.
But the coherence theorem is a way to assign a goal to your axiomatics, right? So here, in this case, you'd say somehow everything. If I use only the algebraic material which is here, then I can reproduce a situation like finite permutation. Something like this.
Yeah, from that, okay. So, but I know that
I'm not thinking about the coherence theorem the way it's presented usually, but it's like, what is it that you're trying to achieve with your axiomatics?
well, what I'm trying to achieve is avoiding all this jargon, basically, and just going to the point of building out a simple toolkit we can reason about quantum mechanics without having to read MacLean until the end. That's basically what I'm about. And to have a way of reasoning about these things without even knowing what a natural transformation is.
Well, another question that may be more physical is,
Yeah, that's what I would prefer, actually.
Is there a time in this somehow?
So at the moment, strictly
Is that in part of what we should read?
strictly speaking, there is nothing you need to interpret as time, but obviously you want to interpret this as this before that. And like something you know very well. So that's probably a point. At the moment, there is no explicit interpretation of anything like space-time, of course.
But you do have precedence and precedence.
You do have.
independence. And also independence.
So you can assign more structure, but typically, if you've got something like this, and you think of them as separate, more space-like separate, and that's why you can move them about and they don't influence each other. It's like implicit in this law where I said I can swap these things up and down, that they are sort of space-like separated. If I've got this, I want to think of them as time-like separated. So now you can just take any sort of causal ordering and you can see where you put composition and where you can put tensor. Tensor then means basically space-like separated, while you can read composition as time-like separated. So in a way you can blow up a causal structure to something like that by actually putting processes between events. So you witness.
So if you move that G on the right up to the very top of the black,
Then of course, then at some point you would think that actually this might depend on this. But that would be additional structure that you need to put in by hand. Yes. So a priori this is very flexible. But you can impose more structure like that at some point. They will actually meet and there might be some dependency. So it's a priori comparable with whatever relativistic consideration you want to make. Is that a very fair statement? I guess so. Yeah. Okay, so now this was supposed to take only 5 minutes. The thing I wanted to get this is just it was not supposed to be, and just what you need to remember is just these 4 graphical elements, nothing else. Forget about all the other stuff we've been talking about. So you got processes. Oh, one important point, we don't assign structure to the symbols A and B. We think just of them as names. So mathematically you would want to think, oh, this is a Hilbert space or something like that. No, they are names. And this is axiomatic, so you don't want to fill in this name with a particular space. And the whole thing about category theory is that it's a theory about processes. So the structure will be imposed on the processes, not on these states, systems, or whatever. We will see there is a notion of state coming out of this. But the real structure lives on the processes. So this is actually so for now just think that we've got these systems, processes, we can compose them sequentially, we can compose them in parallel. That's all for so far. And the laws which they obey are sort of the obvious one, you know, from how do you call it in computer science? Flowcharts. Like flowcharts. You can, or like, you think of it as an electronic circuit, and you can do the obvious things which you can do with an electronic circuit. Think as this, so you've got just electricity wires, and it doesn't matter how long one wire is compared to another. So that's the way you have to deal with this. It's intuitive, it's very easy. You don't need to have all these axiomatics law in the back of your head. Now, okay, so there is one additional element in your category formally, which I haven't mentioned yet, and this is the idea of a unit object. Now, a unit object is an object which is such that if you combine it with the tensor with any other object, then it's naturally isomorphic. Okay, since we don't want to talk about natural transformations, we go to the strictified case and we say it's equal. How do I depict this? So this is an object, you combine it with something else and you get the same thing. How do I depict this? Well, if you adjoin something to another thing and the other thing is still the same, it means you're joining nothing. So you depict it by nothing. It's very simple. So nothing, no line here, some line there. I depict this by that. So this you want to think of as a state. You don't say where it's coming from, but you got it available. So you prepare a state. Yeah? This is a preparation procedure. Now there's an obvious dual concept which has nothing at the output, something in the input, and this you would call an effect if you're a physicist. This you call an effect. And then if you take one of these, and you take one of these, so I've got a state, and I've got an effect, then I get something without an input and an output. And how would you call this? Well, you would call this a number or a scalar if you're a physicist, or a probabilistic weight. It just arises. Now, sorry for those jokes become really bad if you tell them a couple of times and then they become just repulsive. So for some people it's going to be completely repulsive. I'm going to do now. So everybody knows this, yeah? Everybody knows this. So if I close this down, then I get a triangle. Everybody knows this. If I close this down, then I get a triangle. And everybody knows this. And if I close this down, I get two triangles meeting each other. So basically, the three elements you see here is Dirac notation. This is a ket, this is a bra, and this is a bracket. And this is how you produce probabilities, or scalars. Because one of the things about this framework is, like you would say, oh, you need to take the square modulus, but actually this framework doesn't care, because you can just assume that you're already working in that space anyway. So what we're doing, so basically what this language was about, this very simple language with these elements, is just blowing up Dirac notation in 2 dimensions. That's all. That's what has been happening. We have been blowing up Dirac notation into 2 dimensions. So instead of just, like when you write down usually expressions involving Dirac notation, then some of these things you think of as composition, truly. You've got a project, so you've got some projector, you got some projector, you apply it to an input state, then you compute this number, and this is your output state. So first you have input state, then you have a projector, and the composite is actually the output state. You get, so there is, you see there is some sequential reading here. In the sense of doing this composition, there is a sequential reading here, but there is no space on this line to have a second dimension, of course, which would be the tensor. While if you make pictures, you just allow for the second dimension in which you can represent the tensor. So that's basically the idea. Okay, so that's the end of the story now. So this is the background structure against which we will work. This idea of symmetric monodic category, that's what it is. So it's an extended Dirac notation in 2 dimensions. It's an extended Dirac notation in 2 dimensions. Now the idea is to build physical theories with this. So how do you build physical theories? Well, just by being a physicist. You go outside in the world, you observe the world, you do experiments, and then when you get sufficient evidence that something is part of the world, you represent it in your theory. That's what physicists do. And so I go outside in the world and I observe, and my physics history goes very fast, and the first thing I observe is quantum entanglement. So systems can be entangled. Okay, so I have to put this in my theory. So we've got this basic language, and I want to express the ability to reason about quantum entanglement. Quantum entanglement is something about 2 systems, not about 1. So I would imagine that it should be like this. This would be a Bell state, say. I got 2 systems, and I've done sufficient experiments across the Lake of Geneva and all these sort of things to know that there exists stuff like a Bell state, which you can't. So there is no way of sort of cutting this up in 2. We know that it's like a genuine unit. Now, what are the sort of behavioral properties we want from a Bell state? Well, it turns out that we can do teleportation with it. Or something like that. And this is something like this. Because here you've got your Bell state, here you've got the corresponding projection. Now, and then when you combine this in this, so here you've got 3 qubits, A, B, and C. And the result of that is that you've got a flow of information from A to C. They should be of the same type, just forget about that now. Yes?
What about the communication?
Wait, yes. So we don't know that yet. We didn't discover yet that we need to do that. We just post-selected teleportation, and that's where we got so far. That will be another piece of structure. Because, now, I'm doing something here which I haven't described yet. I take a Bell state, and then I put it into something upside down. So this, in my graphical language, is a new operation that for any sort of symbol, which I now depict symmetrical, there will be a new symbol which I refer to as its adjoint. So in addition to symmetric monoidal category, we admit an operation which is putting a box upside down, and we call it the adjoint. And then we get a dagger symmetric monoidal category. So I'll put this down here.
Is there any sense of that acting in like the reverse orientation or something? Because if you're not drawing arrows on these, but implicitly, I guess like A goes to B. So
Yes. So let me put a types here. So I'm gonna keep this on this side. A to B maps to B to A. Yeah. So I'm just representing this by putting the box upside down. Clearly, well, I actually don't have to put adjoint in here if I put F
Because
here.
of the shape of the box.
Because the shape of the box tells you. So clearly from A to B, you go from B to A. And this thing is an involution. It means if you apply it twice, you get the original thing again, of course. That's implicit in the notation. So now we're working with dagger symmetric monoidal categories. And so I gave you the intuition why we want to introduce this thing, and now I'm going to do it more formally.
So there's no sense in which you need to consider like the dual of A and the dual of B or something, or are they self-dual, or?
What do you mean by dual? I can't even use the word at the moment yet.
I mean, like if I have an operator on a vector space, if it's adjoint, then that's an operator on the dual vector space.
No, it's not.
It's not?
It's not, no. Transpose is in the dual, not the adjoint.
Okay.
Okay, so there's a small board, but I need to speed up a bit. So I'm gonna do. So this is now the basic background structure, where you have this dagger symmetric monoidal category, which is just expanded direct notation. Now, with this element, which is still an element in direct notation, we can turn cats into bras. So this would be like turning a cat into a bra. Yeah? So this is an element of standard direct notation. Now here, the first thing I want to introduce is like this entanglement structure. Secondly, I will introduce classical structure, because we need to make this classical communication explicitly. And as a third layer of structure, I will introduce complementary structure. Since we know that complementary observables are very important for quantum behavior, you want to do key exchange or something like that. So these are three layers of structures which we want to put on top of that. The first one was jointly developed with Samson. The second one with Dushko. I can just be a bit informal here. Samson. Dushko. And third one with Ross. We will talk about this stuff. Dushko will talk about this stuff too here, I think. So what is entanglement structure? Entanglement structure simply, as I denoted it, is an additional piece of data which we call an entangled state, yes, and which satisfies this equation I just drew down before. Now if I'm really smart, since this is a very special object, it's a very special thing, it's a structural element, it's something which I add to, so it's like a Lego box. We've got these boxes and I'm adding this new element. I'm saying my theory has to include this thing, such a triangle, and to denote how special it is, I will represent it by a cup. I will represent it by a cup. Yeah? Now remember the equation I put down before. So this was this equation, I had a cup, I had a cap, I connect these, and I create this. That will be my axiom of my theory. My only axiom of my theory.
Bob, if you have different type of entanglement, something is maximally entangled.
So that will be a consequence. At this stage, it's just
So when you say that this is one of my axioms, you actually implicitly see that you have maximal entanglement.
no, this one is. It's only one.
Yes,
It's
so that's
only
why
one.
no, but that's why the teleportation
Yes,
works.
yes, I assume that I've got one maximally entangled. Yes, so this is implicitly in the definition, it's maximum, and implicitly it's also the Bell state. Because otherwise this wouldn't be an identity, but something else.
But that symbol, you cannot use it for any type of
No,
entanglement.
it's very special, it's only one. But easily you can produce other from this. We'll see how this works. So okay, I think this has been long enough, so this goes.
This is kind of the same question as before, but with that axiom, does that mean that you're washing away normalization?
So the thing is, these things are typically not, normalization is not washed away, because there are numbers, there are scalars, so you can actually read out the scale. It turns out that in the specific case of Hilbert space, this thing, which is the composite of this bit and this bit, will turn out to be the dimension, for example. So there are genuine numbers. For structural reasons, it turns out that it's better not to normalize the state. But you can normalize it because you've got scalars in the theory. So the length does play a role. But it's just that this would become much messier as an axiom if you do this. So for a lot of practical purposes, like for example building the trace, because from this you can build the trace structure, you only get the right values if you don't normalize this one. So if you would treat it really as a Bell state, you want to normalize it. So
Maybe just to amplify exemplify that one piece of racing, if you tried to teleport through a state that didn't have a uniform marginal in quantum mechanics, you would probably unavoidably disturb the information, even if you recovered it by sort of redistorting the marginal to be uniform, right? You would decohere a little bit?
Yeah, well, what I was meaning more just that if you actually project on the Bell state, what you would have there would be equal to 1 over the dimension times the other.
Oh, yeah. But this doesn't have
But
to
since
be,
these are, yeah.
I mean, with probability 1. That would probably can't be version 1. But it's still, I think if you went in the quantum case and you didn't care about the normalization being maximal, the success probability being maximal, you would at least, it would still have to be proportional to a Bell like state. You have to have a uniform margin. I think that would be the thing that corresponds to being a triangle.
Okay. So,
Can I give some comment?
Yep.
I think you'll look here at something which is axiomatic. So forever there will be something missing. That's the point.
Yeah.
That's kind of it's a converging process. And in the end, the perfect world is the standard model. But the point is not to reproduce the standard model, but to produce some sort of algebraic room around it.
Yeah.
Well, in the way you're doing with Alex. So forever we can stand at this and we can say, well, you cannot do this, you cannot do that. But that's the point in a way.
But
measuring how much you can do, how much you can replay, and with what axiomatic cost. It's part of the exercise.
It's part of like identifying some structural resources in your theory. When you look at Hilbert space, it looks like a very plain thing. It's very hard to see how you can decompose it in other little pieces of structure. But this is basically what he's doing, as we will see. We will get very close to things you do in Hilbert space, like in Rosenstock. You will. I don't want to spoil the fun. So, but you will be doing things which, for example, in quantum information have appeared in quantum computation have appeared in very recent papers as new results within this language. So you can do genuine reasoning. Let's put it like that. So, but I don't want to spoil the fun of
But I just thought it was a little bit important to see, when you introduce one piece, go to the quantum setting, see what you've introduced, and that
Yes,
helps you
yeah,
understand
sure.
what you just did.
So, yes.
And I think this is like, the state has to have a uniform marginal so that you can teleport through it
Yes.
without disturbing you.
Yeah.
And
But it
another
could be subnormalized.
Yes.
And another important thing to say, I think, is that there's no unique way to obtain that decomposition. And perhaps even within this kind of decomposition, you could introduce one of the elements before another one.
Oh yes, yes. I'm just. This is because I'm used to tell it like that. So
you could put classical
as,
structures.
as we will see, yeah. That's for example. This will be a consequence of actually the classical structure, for example. So things go. So this will not be something new, but this will be refinement. Each step I will make here, which I probably won't be able to do, will be a refinement step rather than adding. I will refine my structure and new things will emerge. So now let me just.
I think you referred to this before. It's as if you've chosen a unique, a distinguished basis.
No.
Because
Keep that in mind. No.
Well, at least you've chosen not quite that, but you
Not
close
quite
that
that.
because you have
We will-
these two systems.
we will see.
and you made
The next
a
step will
unique
be basis.
identification between
A basis is
space of
more
one
than
and
this.
space
A
of
basis is
the
more than this.
Okay,
And we will
it's a
see
little
this.
bit more, but
We will see how it is.
I'm saying, okay, but
Yeah.
the point I'm asking about is, by that entanglement, someone referred to this before, I think, you made a unique identification.
Yes.
Between,
But that doesn't really.
That's
That
not-
doesn't need specification of a base yet.
well, if you give a basis in one, it'll produce a basis in the other.
Yes, but if
So
you
it's
don't have
half-
it in
it's
one-
half a specification of a
We'll
basis.
see exactly what it is.
You don't have independent.
We'll see exactly what you need to get a base out of that. That will be my next step. Exactly identifying the concept of a base in this way. So
But I'm asking whether you're going to do some extra structure now by giving this unique identification.
that I will do. That's the classical structure there. Will be exactly specifying a base in this language. Will be exactly that. And this will be a consequence of it. This will be a consequence of it. So that's probably your intuition.
No, but I'm not, yeah.
Their answer would be that this usually thing that you do there really is between A and the dual space A star.
Yes, and then it's completely base independent.
But only right, and that's
Well, even if you make a map between the space and its dual space, that's some extra structure. There's no canonical map between
There is a canonical.
vector space
it's
and
not a map
dual space.
between the two. This is a map from the tensor unit to a tensor A star, and that thing is.
That thing is canonical. So for formally this is a map.
Then why do you call this both A? I don't understand.
Yeah, well, first, yeah, okay. Let's call this A star, and for all practical purposes, forget that there is a star. Okay, let's call this A star. And then think of it as a dual spur for now. So, there is a, yeah, okay, I don't, so, and formally this thing would map just the unit on the sum of, where you read this one in the ordinary space and this one in the dual space. And then this thing is canonical. This is completely base independent. So, it has a tiny bit of base independency, and in this way you get rid of it, basically. So what I want to prove is the following. Given any operation f, I can actually build this thingy. Yeah, I can do this. This is part of my language. And I will call this the transposed. And now it might be even useful to introduce these A's. So if this is A and this is B, then this would be A star and this would be B star. So the transposed lives in the dual space, referring to a comment made before. So the transpose does live in the dual space. So the choice which I made here was, because I'm axiomatically, I've got some more freedom, I can just say, okay, I identify space and it's dual space. But for now, given the model, it's probably simpler to think about it like that. Now, what can I do? So I've introduced this new thing, and I join a wire there, I join a wire there, which gives me this configuration where the transposed is now written as a 180-degree rotation of the initial one. I represent this transposed just by taking this box and rotating it 180 degrees. It's a notation, nothing more. Yeah? What I can do now is, so this is the transposed. I'm now going to fill in its prescription, which means that I've got this box here in the middle representing this one, and now with my axiom I can yank this wire and I can yank this wire. Yeah? This was my axiom, that if I've got something like this and something like that, I can stretch it. If I've got something like this and I can something like that, I can stretch it. That's what's written down here. As a result, what we get is and so the basic idea which you see here is it is as if you can take this box and just slide it over these wires. Yeah? And slide it further. So this 180-degree choice is very smartly chosen, because it sort of allows you to slide these wires in a nicely geometric. And so this is a lemma. This is a lemma which I just proved. I can slide boxes across wires. Okay, now we will use this lemma to prove something else. Consider now the following configuration. Alright, this is wrong. Yeah? And I put a box here. I have to be careful. And I put a box there. So I can take this one, slide it there, and then what arises here is something of this shape. Yeah? If I slide this. Yeah? So this would be the adjoint to this one, because that's how we define the adjoint, upside down. And now if we pick f such that its inverse is its adjoint, which in Hilbert space means is unitary, unitarity means the inverse is equal to the adjoint, then of course these two cancel out. Yeah? These two would cancel out. So this whole thing would be equal to an identity. Yeah? Yeah? Okay. So now let me introduce my triangles again. Yeah? And I'm going to introduce two parties. Two parties. I call this Alice. And I call this Bob. Yes? Now you see, you've got here a Bell state, here you've got a Bell state, there you've got an effect labeled by F, there you've got some unitary labeled by F, and the sum of the whole process is the identity, meaning whatever comes in here goes out there. So this is teleportation. Yes?
Except that F depends on the outcome of some measurement.
There is a correlation. So we know that this thing cannot be imposed in a deterministic manner, of course, because it's an effect. It's part of a measurement spectrum. So there is a label F here, and there should be a correction there, corresponding to whatever measurement outcome you get here. So basically, there is a communication from Alice to Bob going on, classical data, because this F should be the same as this F. So far, there is some classical correction going on here, but it's implicit. It's not like an explicit structural part of the theory, because it's correlation between labels. Yeah?
Could we say the thing that makes that canonical is that there doesn't have to be a correction?
What?
We say the thing that makes one of those Bell type states canonical is that there does not have to be a correction in that case.
For example, yeah, for that one you wouldn't have a correction. That would be one special one in which you put, like in the Bell base, typically one of these would be the identity. Yes, and that's that example. So basically what this lemma allowed you to do was like transfer the correction from here to there. So that gives you, now the thing we now really want to do is to make this guy explicit. This is just now an implicit presence as a correlation between this symbol and this symbol. It's not like a structural part of our theory, meaning it's not a morphism in the category. It's not a box in our language or a line in our language. So and that's what's going to happen here, and that's exactly where basis will be coming in. So we will now need to introduce a new structural element which allows us to make this line explicit. Classical communication. And we really want to have classical data and quantum data as part of one formalism. So they need to live in the same category one way or another. So that's the point, the thing we want to achieve now.
Bob,
Yeah?
I've got a preliminary question, but you can brush it away if you don't have time. When you're fixing the notion of adjoint, if I go back to the initial, the standard model, you're actually choosing an inner product. So, and there
yes.
and there are many ways to do that. So
it's fixing it.
you're
It's
fixing one,
It's fixing one.
and therefore the relationship you have to the standard model is that you can embed you can see the standard model in many ways as an instance
Yes,
of this
by
structure.
different choices of inner product,
All right.
of course.
Okay.
So you choose an inner product, and at the same time you choose unitarity, because that's what I was using here. I pick my F such that it's inverses its adjoint,
Right.
which is of course choice of inner product. Okay, so this was teleportation. And now the idea is to get some grip on classical data. Now what do we know about classical data? Well, we know something very particular about classical data, the fact that it can be copied and deleted. So this is like, I put it like a bit different. I don't say there is no cloning theorem in quantum, I say there is a cloning theorem in classical data. There's a cloning fact in classical data and a deleting fact in classical data. So we want to make a positive theory here. So we want to say that things can be done rather than things cannot be done. It's a structural theory, it's a structure. So you give witnesses for what you can do. This is the kind of mathematics you do. You give witnesses for what you can do. So we need to introduce a witness for the fact that we can copy and delete. Yeah?
We could call this substructural physics, right?
Substructural physics.
It's a fun because we call it substructural logic in logic. When you don't put into the axiomatic the ability of duplication, we call it substructural. Because deleting and copying are called structural rules.
I should put them here. Yeah. So we introduce two new boxes. a copying map, which I'm going to cover, and a deleting map. So here we had sliding as a lemma. And teleportation. Oh, okay, let me just come back here. So I just introduced this bit of structure, and it seems that all you can do with is teleportation. I should stress, I'm not going to talk about that. I don't know whether Peter is going to talk about that. But you can actually, this is enough for you to construct completely positive maps, mixed states. Like if you take a smaller category, the category of Hilbert spaces, then this little bit of structure is enough to produce your completely positive maps and to produce your mixed states. And you've got a trace structure. You have trace structure which you can produce probability. So the CPM construction is. Are you going to talk about CPM? No. So there is a lot of stuff you can actually do here. So you can prove a no-cloning theorem purely based on this structure. This is Samson who is not going to talk. Samson, attention.
I'm not saying.
Are you talking about this? No, you don't know what I asked.
Yes, I do.
What? You talk about it. Cloning, deleting.
I don't know.
No, fuck me. So anyway, so here you got already no cloning, by the way. So this is so part of the ideas with how little structure you can prove, you can already build or prove how much. So here you've got teleportation, you've got things like obviously entanglement swapping, logic gate teleportation, no cloning, CPM, completely positive maps. So all these things which you wouldn't expect at first already live in this very general, at the level of this very general structure. So now we're going to include, and there's no basis or anything like that here. There's no concept of basis whatsoever. Sure. So I shouldn't, it's obvious, but just there is nothing like an additive structure here. There's no concept of addition whatsoever going on here. Just to stress. So, but you can do things like completely positive. You can construct completely positive maps without a concept of addition or anything like that. So that's the main idea. Okay, so now we go further, and we want to express the idea that we can, if we are dealing with classical data, copy and delete it. So this would be my copying map. This would be my deleting map. Yeah. Now, what actions do we put on a copying and a deleting map? So how do you do? Well, you build your copying machine and you see which properties it satisfies. And then the sort of properties, you can see is that, okay, you take some input, you start to copy, then you copy one again, and you get 3 outputs, and then you do another experiment in which you copy some input, and then you decide to copy the second one instead of the first one. Obviously, these things must be equal, and will be equal. You will observe that if you got a decent copying machine. So other things, if you copy and then delete, then you just get the original back. So like sort of obvious things you will know, and then if you swap your copies, you will again just get 2 copies of the thing. Yeah? So, well, this formally, these axioms composed on these 2 symbols is what is called a commonoid, a commutative commonoid structure. It's a for somebody who doesn't know category theory, it's a bit of a weird concept. Because you recognize the words monoid, you recognize the words commutative, and monoid implies associativity and having some sort of unit. But the problem here is that the type of this operation is not like a multiplication. It's not a multiplication, it's not something. This would be a multiplication. Take 2 inputs, you get 1 output. This goes in the other way around. You've got 1 input and 2 outputs. So it's a multiplication upside down, which is called a co-multiplication. The unit is also upside down, so it's a corresponding co-unit. And so this is a monoid, a commutative monoid upside down. But you feel if you're dealing with something like copying operation, this is the natural structure it satisfies. It's not a, and the way to put it down, this is not an algebraic structure. This is a co-algebraic structure. And there is this big field now, which is very popular in computer science, which is called co-algebra, and it's looking at things upside down. And I think Prakash, for example, co-induction. You invented secretly co-induction, and it's a bit
Secretly, very secretly.
very secretly. Nobody knows about it. So there is an upside down definition of induction, which is called co-induction, which is a completely different thing.
Yeah, but yeah, I mean, those kind of co-algebras shouldn't be confused.
Well, no. It should be, this is doing things upside down as you do it in algebra, whether it's like a general co-algebra or not, it doesn't.
Mentioning quantum groups is an example where you see.
In quantum group theory, these things have occurred. But I think the better example is the notion of quantum measurement. Because a quantum measurement, what does it do for you? You get an input and you get two things out. You get an input, quantum system, you get two things out. So you got some sort of branching structure. More, and if you do another measurement, something more comes out. And the idea of structures which branch, rather than say, multiplying, are always living in this sort of co-realm. More or
This is
less.
very different than what happens in quantum groups, right?
That's why I didn't want to give this example, because it's sort of, again, a different... The flavor here is about the branching structure. Of course, many mathematical structures occur in many different contexts, but I want to stick here to operational notions, not sort of fancy mathematical physics.
People probably do know this kind of co-algebras from Swidler book and anything.
Who read Swindler book? Swidler book? Who read Swidler book here?
I read two.
So yeah, that's a minority, so we don't care. Okay.
Actually, everybody learns co-algebras when you take quantum mechanics and you add angular momentum.
Yes, but they don't call it like that. Yeah, okay, yes. So, but anyway, so I think this is a monoid. You can't have a simpler algebraic structure of monoid. You have an associative multiplication and a unit. So this is this is as simple but upside down. This is as simple and upside down. A lot of mathematical structures probably, I don't think people understand this very well. They have both an algebraic and a co-algebraic aspect to it. And I think it's very not understood. It's not really well understood even, I think. Yeah? Yeah, okay, yes, that's true, a bialgebra. Okay, we're going to hear about bialgebras. And that's an algebra and a co-algebra. It's not like one thing which is sort of both. Frobenius probably has both. Yeah, Frobenius has both. Actually, this thing has both. So we've got this comonoid structure, which is an obvious structure on copying and deleting. Now, so what we wanted to do was, of course, seeing what other properties does classical data have that you can actually describe protocols with the properties you usually want to attribute to classical data. And it turned out that we needed to use the following very weird equation. This is called Frobenius identity. So here you've got your copying operation, that's the thing upside down. Here it's there and there. So types match, there's two inputs, there's two outputs on each side, and this thing is equal. Now, you wouldn't think of this as the first thing to write down if you're talking about classical data. But it turned out that two guys, Carboni and Walters, like a lot of the category theory, if you read the category theory textbook, then you get Cartesian categories, Cartesian closed categories, loads of topos type stuff, all kind of this. And basically what people are doing is axiomatizing the category of sets and functions. Yeah? Because that's where you get all these topos and all this sort of stuff out. Now, these two guys, what they were looking at was the category of sets and relations. So it's a slight modification. You go from functions to relations. And nothing which you ever did, or the sort of structures like Cartesian closures which you assign to sets hold anymore there. In essence, other things happen. And this is what they identified as the crucial law governing relational calculus, basically. And now, how does this work for relations? Well, you put here a 0 and you put here a 0 here. This would be the copying operation, copying relation. So it sends 0, 0, 0 to 0, 0. So you get 0, 0 out here. Now, if this is a relation, then it has a converse. That's one of the reasons this doesn't work in functions, because if this is the relation which sends 0 to 0, 0, 1 to 1, 1, then you can't have a converse to this as a function, because functions in general don't have converses or inverses. Relations do. So this would be the converse relation, and what does it do? It sends 0, 0 to 0, 1, 1 to 1, 0, 1 to nothing, 1, 0 to nothing. Yeah? The obvious converse relation, so 0, 0, 0 would go to 0 and 0. Here you got the same thing, 0, 0, 0, 0, 0. Yeah? Now, Same thing holds for 1. Let me now put in 0, 1. Then I get 0, 1, 1. 1 goes through, but here nothing goes through. So no output, no output. 0, 1. Nothing goes through, because here already a conflict. So this law holds for relation, and this doesn't depend on the fact whether I'm talking about two-element sets or whatever. This is like a general law which holds for relation for some reason, and which embodies this idea, which gives a lot of properties. It's called Frobenius identity, and it turned out that is exactly what we needed, because I didn't know about this Frobenius. I don't read papers, so I didn't know about this Carboni-Walters paper until somebody told me about it when he recognized this law. So this was really what we needed, and I found it by brute force. So what do we need to describe protocols on the classical data? Now, the magical thing is now going to happen. And this is part of the reason I avoided writing down these duals, this A star. So this is like maybe the biggest piece of magic in this whole presentation. So, we've got this little operation here, which we can also put upside down. So, if I plug it in here, now this is a bad piece of... if I plug it... this one is nice. This is a nice one. Music. And I plug it in here. Oh. So this was the unit for this multiplication, co-unit for this co-multiplication, so the whole thing here becomes identity. Yeah? And now, look at this. We can actually join them together and compose them into one piece. Do you recognize this one? This was the one we started with. Huh? So, you got this big triangle, and this gives the identity. So, what this means is this new structure here, it was this commanoid plus Frobenius actually is a refinement of this guy. Now how does this work in overspace? So that's clear, everybody sees this, that this pieces of structure I introduced here refine this bit. So basically the way you have to think about this in terms of models is that here you're talking about spaces. Like, you're just talking about Hilbert spaces and the way you combine them with the tensor product. You don't care about anything like a notion of basis. And what this introduces is exactly a basis. This thing introduces a basis. And here there's a genuine theorem here. I think this is the first theorem I mentioned. A theorem. And I should put names on it. So that's me, Dushko, and Jamie, who you surely will hear a lot from the whole week, because now he's silent, but usually he's not sitting there. And the theorem states that if you look at the category of Hilbert spaces, and you look at all the, I should say, should be sure I don't forget anything, combinations of morphisms of this type, like something from A to A tensor A, and something from A to the unit, which is the complex numbers in the case of Hilbert space, which is a commutative commanoid, satisfies this Frobenius equation, and then satisfies another normalization condition, which basically makes this operation an isometry, so which is this. I haven't mentioned it now, it's not that essential. So this should also be equal to identity. It just means it's an isometry, this operation. That's what it says. You want this to be an isometry, which is this is equal to identity.
Wait, sorry, you have that in your basic equation system?
Yes. You need you need it. I know from topological quantum field theory, this is not, but we are not doing topological quantum field theory. Here it's essential, really. But it's actually a normalization condition. Topologically, it's of course big. You turn a circle into nothing.
It says that identity is the unit for convolution.
Yeah, I understand that. Yeah.
Yeah.
So what do you get if you category of Hilbert space?
In the category of Hilbert space, if you've got a commanoid structure, it's Frobenius, and it's this. Essentially, it should be commutative. Then you are in one-to-one correspondence with bases. So a base. What you get is a base. Exactly. And how does this base look? How does this base look? So this is an axiomatization of bases. This thing is an axiomatization of bases. So that's why I was saying we'll hear more about bases.
Axiomatization, it captures in Hilbert spaces what the base is.
So yeah, so it's an axiomatization of bases, I would say. Anyway, let's say, how does this look in Hilbert space? Suppose you pick a base. Then this copying operation will just be copying the base vectors, and the deleting operation will just be delete the base vector uniformly. Now everybody knows that this only copies base vectors and nothing else. If you take anything else here than a base vector, what you get is not two copies of it, but you get some sort of entangled state. Yeah? Similarly, it wouldn't uniformly delete any other base either. So clearly each base, and you can check that these equations, that these linear maps, now these are linear maps, always satisfy this equation. So the big deal is that conversely, anything which satisfies these equations always rises in this way.
Sorry, the very last one is only satisfied up to normalization, right? There's an extra factor of n.
No, it's not. If you go from I to I, and then the adjoint to this is just mapping this back to I. So I goes to I.
It's not the Bell state going.
Yeah. But this is this thing is not normalized. This thing is not normalized. The adjoint. And that generates the non-normalization of the Bell state. So clearly, if you the thing to do now is, if I call this delta and this epsilon, then this initial Bell state is nothing else than delta after epsilon adjoint. That's like this Bell state to start with.
But also, Bob, I don't think it is quite in one-to-one correspondence. And I think you can forget about that condition there, because you can't make that one-to-one claim anyway, because you can multiply these basis vectors by e to the I theta or something, and it'll still be copied by the same thing, but you'll get a different basis.
No, it doesn't work anymore if you multiply this with e to the I theta, because here you get...
Oh yeah.
It doesn't work. You should know this. You proved the theorem. I've been challenging you on the proof, and now you're challenging me. So the way you prove this is basically you pass. So you look at. Are you going to talk about this?
Yeah.
Are you okay? So I'm not. So Jamie will probably talk about this proof.
So is this a way of constructing a Hilbert space out of a vector space?
No. It's like there is no difference. The order it doesn't go like that, because the moment we introduced an adjoint, we actually are already closer to Hilbert space than to vector space. We already fixed it in the product. The thing is, we fixed it in the product without actually having a vector space structure. So this part is actually an inner product without a vector space structure, sort of, which is a bit weird, but that's what it is. And here you add bases, and the moment you add bases, we still don't have a notion of sum, but we have a notion of bases, so a fixed basis. So things just go a little bit differently than how you usually axiomatize things in linear algebra. But it seems to be operationally making a lot more sense to do it like that.
Well, instead of the notion of sum comes the change of base.
At the moment there is nothing like change of base.
Well, if you add a unitary on it, you get...
I didn't add a unitary.
That's another base.
Well, it's not there yet, so... Okay.
How do you fix an inner product for a vector space that doesn't...
Huh?
How do you fix an inner product without a vector space?
But that's how you do it. I can't say anything more, that's how you do it.
Bob, are you going to wrap up soon?
Yeah, I'll wrap up.
So do you have models for this category other than Hilbert space?
Yes, so that's what I would have liked to talk about, but won't have a chance to talk about. I'm sorry. Sorry, he's guilty.
In the evenings overrun, we can talk about it.
So I could, yeah, if somebody's interested. So like, I'll end up with just mentioning the models, not describing them. So the final thing I wanted, so here, the really appealing thing about this was purely its graphical interpretation, that it was just like yanking a rope. While here, this was just a bunch of axioms, which are operationally justified, which gave this nice connection with this one. It's like really passing from a Hilbert space, where you've got some notion of inner product, but nothing else. So all the rest is thrown away, except your inner product. And here you adjoin the idea of having a basis. So that's all nice, but like, is there some graphical interpretation here too? And that's the second theorem, which you find in different areas in the literature very similar. So it's not really that original, but it's due to Eric and I in this form, but there are similar things which are very related anyway. And which says the following weird thing, that you remember I introduced this triangle and I said because it's a very special one, I'm going to give it a different notation. So I'm going to do the same here. I'm going to put a dot in the middle, a dot in the middle, a dot in the middle here, and like this. Yeah? And then the theorem says as follows. If I combine, so I should also introduce a notation. As a notation I introduce the following idea. Yeah, Eric is the scary guy there.
Thanks.
One of the
The other one's at the blackboard.
So this is a notational convention. You see, I can sort of develop this further. This is something I can build from these things and these things. I can build this side, and I'm just going to, whenever I've got something like that, with n inputs and m outputs, I'm just going to represent it as the spider with n inputs and m outputs. Just a notation. And then the theorem says that whenever you plug all this stuff together, in any way, using adjoint composition, with only restriction that the graph you get, the picture you get is connected, so it doesn't exist in two pieces, but just is one piece, then it can always be rewritten in this way. So basically, and actually it turns out that all these axioms, which I wrote down here, are just consequences of this principle. So this characterization as a spider is equivalent basically to this definition. Now, so this is basically, this says whenever you got some very complicated diagram, you reduce it to a spider. And this is of course a way to establish equations between different diagrams. For example, that's the last thing I'm going to do. For example, if I start with this, this is clearly equal to this. Yeah? I don't know whether it's readable with, oh, I should take another color, I guess. And this is clearly equal. Yeah? Because the number of inputs is equal on both sides. And so here, this thing actually, I can contract into a single dot because of the spider principle. Yeah? And a single dot on a line we're just going to erase. Because we done it. And so you find the row-Yanking principle as a consequence of the spider principle. So the spider principle refines the idea of yanking a rope. So it's just a more refined way to compute. It allows you to do more. It's better. So I don't know whether anybody's going to talk about this. I don't think. Jamie, you're probably using this, I guess.
Yeah.
Yeah. So we'll probably hear more about Jamie. So okay. So.
Is this the question to Jens? Are there other models?
Okay. Wait. That's wait. No. So.
Ross going to speak about Ross.
So Ross is going to speak about Ross. So clearly, so here we just got the idea of one base. The whole point about quantum mechanics is having more than one. For example, complementary bases. And once you introduce complementary base, so I didn't say what you can prove a lot of stuff in this. Like you've got POVMs, you can prove Neymark's theorem at this side. This was a result also in Paris. So you can do a lot of stuff here more than you can do here already, obviously. But to do the real stuff, you need at least two complementary bases. And that's what Ross is going to talk about, I think, when? This afternoon? This afternoon. Now about models. So this is axiomatics. So this is a very general scheme, which obviously Hilbert space is a model of, in the sort of obvious way. Another model is a category of sets and relations. Category of sets and relations. Let's stop here, let's stop here, let's stop here. So category of sets and relations is a model of this too. And you get, there are canonical bases sitting in the category of relations which are just induced by the underlying sets. So basically, all the things we prove here, you can prove with just for relations. Now, another interesting model, which some people know, is, for example, there is this toy model by Rob Speckens. Rob Speckens' toy model is a category. You can write it down just as a category in 3 lines, and everything here also applies to this category. So the idea that you can build completely positive maps, POVMs, and what in Rob Speckens' model are just consequences of the general axiomatic scheme. I think so, if some people want to hear about this, there can be an evening session about Rob Speckens' model in this language, and then like the sort of complementary observables he finds are exactly those in the sense Ross will be talking about. So Rob Speckens' model is just an instance of this. And then there is an even cooler model I'm not going to talk about, which is an even smaller model than Rob Speckens, which has a lot of quantum features, and which basically fell out of looking at the Rob Speckens model in this way. You can actually go to even smaller discrete models with loads of quantum features. So that's something I could talk about somewhere in the evening. But that's it.
Okay, thank you, Bob. So, I guess you're about 10 minutes over.
Only?
Only.
I thought like this.
So, and there's lots of time for people to have conversations throughout this week, so I vote we put Peter on next. Have questions later. All in favor?